Hello again, this is at THS Mr. Jones with chapter 4.2, which is higher degree polynomials. Okay, so our objective is to understand zeros in behaviors, intermediate value theorem, which will probably be something new for you, and how to graph polynomials bigger than degree 2. Okay, 4.1 dealt with parabolas, which is degree 2. Okay, graphing some sort of quadratic or parabola. Now we're going to get into higher degree polynomials, which we've talked about some of them before. So I first want to kind of go over a definition of a polynomial. So polynomial is in any form a(n) to the xn plus a(n minus 1), x to the n minus 1, minus 1 plus, I go all the way down to a2x2 plus a1x1 plus a0x0. Okay. And we need to make note of what this n value can be. So n is a positive integer. Okay, so it can't be, we don't want fractions, we don't want negatives, we don't want anything like that. So let's look at maybe some that are polynomials. So if I give you this, that is a polynomial. I can give you this. That is also a polynomial, or that is also a polynomial. So something that would not be a polynomial would be something like this. Okay, because this would be a -1 exponent. Something like this, because we've talked about how the radical is just a fractional exponent. Okay, so we also want to talk about degree. Degree is the highest exponent on your variable. So like this here, the highest one is a 5, so that would be degree 5. So this is degree 5. This one, I don't have an x, but if I did, it'd be x to the 0, so that's degree 0. And then this last one here, we would have to FOIL this and distribute. Okay, so when you got all that done, it's actually degree 7, because you get 5 from here, and then when you take that times this squared, you'll get a total of 7. So, but we'd want to distribute that and get that out. Okay, so degree is the highest exponent there. With polynomials, we have what's called continuous functions, or continuous and non-continuous polynomials, and then we have smooth and non-smooth. Okay, so let's look at what each one is. So I can have, we'll just draw out 4 here. Okay, so we're going to graph 4 things here. Okay. So this one here, because it makes this jump from one to the next, okay, you're here and then you have to pick up your pen to continue. This is not continuous. Okay, to be continuous, I have to be able to draw the entire thing without picking up my pen or pencil. Okay, so even if it's just a hole, maybe I got to do this. Maybe I have this. Okay, that's a hole. So I would be drawing here. I'd have to jump over that number and continue on. So this again is not continuous. Okay. Now, smoothness is kind of like measuring the curve, the smoothness of a curve. So if I do something like this, let's just draw the McDonald's sign there, okay? Because this is a sharp bend, okay, we call this maybe a corner or something. It makes a sharp turnaround. It is not smooth, okay? But it is continuous because I'd never pick up my pen drawing this. So then we have something like this. And a graph like that would be ideal because it is smooth. Okay, I don't have any sharp bends or corners. And it is also continuous. And these are the types of graphs that we will study in college algebra. We'll do some non-continuous ones. Those are more like piecewise functions and that kind of stuff. But for right now, we're going to focus on these smooth and continuous functions or graphs. Okay, we have what's called a power function. Okay, so this is my power function, and it basically just kind of outlines our parent functions. So I can have anything from like x1, x2, x3, x4, x5, and we can keep going on up. And we can group these into odds and evens. Okay, so I've got them grouped up here. And we're just going to look at some characteristics if it's odd or even. Okay, so let's just look at the basic ones here. We'll look at x squared and x to the third. Okay, so we might look at x squared for this one and x to the third for that one. So we know that a square is some kind of parabola, and then this cubic is this S-looking thing that we've talked about. So what kind of symmetry does it have? Well, this parabola, my line of symmetry is the y-axis. For this, it has symmetry about the origin. Okay. This is domain and range. So my domain of this is all reals. My domain of this one will also be all reals, as long as they're continuous. My range, if it is even, for just the parent function, starts at 0 and goes up. But for this odd function here, just this cubic parent function, it is everything, all reals again. Now, some key points on this graph. So for an even, a key point would be 1, 1, 0, 0, and 1, 1. Okay, those are some basic key points that are on the even parent functions. Okay, for odd parent function, we'll have -1, -1, 0, 0, and 1, 1. Now, these aren't the only points on there, but it's just a base point to start at. Okay, just a 0 and then positive and negative on both sides. So where's this graph right here increasing? It's increasing from 0 to infinity. This one is always increasing. When is this one decreasing? Negative infinity to 0. And this one is never. Okay. It is never decreasing. It's always going up. And I believe I had at one time talked about the progression of polynomials. I think I call it the evolution of polynomials. So where you start out at x, x squared, x3, x4, x5, and we'll go to x6. So x was just our basic line. Okay, x squared was our parabola. X to the third, we had our little s in there. X to the fourth, we could have something like this. X to the fifth. and then x to the 6. Okay. So this degree up here is just kind of telling you how many turnarounds we have. Okay, so we start here at 1, x squared, x to the 3rd. So I've got 3 different turnarounds. Okay, here I could have 6 different turnarounds. So 1, 2, 3, 4, 5, 6 different turnarounds. Then I can keep going up. Now, does an x to the 6 have to look like this? No. In fact, an x to the 6 could look something like this. Okay. It does not have to have all those humps. All right, so let's graph f of x equals x minus 1 to the 3rd. And we'll kind of use what we've talked about before. So let's identify the parent function. Okay, my parent function is x to the 3rd because I've got that cubic. And what does that mean about my graph? Well, my graph originally will look something like this. And we notice what happens to this parent function. So that's the song we've talked about. What does this minus 1 in here do? Well, that minus 1 is h. So we say the opposite of h goes left and right. So this one is going right 1. So we're going to take this. We're going to go right 1. And then everything stays the same. So in the end, I will have something similar to that. Again, some of you are getting into doing this on a graphing calculator, which is awesome. Okay, so we'll graph there, and we'll notice here my graph looks similar. Also make use of the table. If you need to change it to input ask, do that. So then I can just input some values, okay, and see where we're at. Now, these key points up here and these domain and ranges were only for the parent functions. So when I do something like this, move it right, the domain and range of that would also change. Okay, domain is still all reals on the x, all reals on the y, and I'm always increasing. But for here, if I have something like this, that will change. So real zeros of polynomials. So if x equals a number, so we'll say is a solution if f of x equals 0. Okay. So if I take that number and I plug it in and I get 0, we call that a solution. Okay. And then our number comma 0 is an x-intercept of the graph. Okay. So that's where this number up here is where it crosses the x-axis. And we can also say solution or root up there. We say x, our number is a 0 of f of x. And then x minus our number is a factor of f of x. Okay, so all 4 of these things are talking about the same thing. So you have your factors, your zeros, your x-intercepts, your roots, and your solutions. All 5 of those are talking about the exact same thing. Okay, so we need to know how to factor in order to find the 0, in order to find the x-intercept or the solution or the root. Okay, intermediate value theorem. Okay, super, super awesome theorem. Okay, it does not work all the time. Okay, and I'll show you a case where you can't always find the zeros using it. But it works awesome. Okay, so a and b are real numbers, and if a is less than b, and f is some function. So I've got some function here, and let's say this is a and this is b. Okay. If f of a, meaning your y value here, so y, and f of b have opposite signs. So meaning this is positive or this is negative or this is negative, that's positive. So in this case, this one's negative and this one's positive. Okay, so they have different signs. Then there's at least 1 0 between them, which would be right here. Okay. So there's at least 1 0. Okay. Does it tell me what the 0 is? No. Okay, but I can use other methods in order to find that. Okay. I can keep dissecting this in half, and we'll talk about that later and seeing how the sign changes. But if the signs are opposite, there's at least one. Okay. Now, does that mean if the signs aren't different, there are none? No. Let's look at this graph right here. If I take this graph and I choose this A and this B, okay. Well, the signs are opposite, but I've got 2 zeros between those two numbers. Okay, that's kind of the downfall of it, of the intermediate value theorem, is I can't always tell, you know, if I got A and B and there's the same sign, there could be a 0 between those two. Okay, 2 or 4 or 6 zeros between the two. Okay, also, let's say I have, here's my graph. Okay, let's choose this one and this one, A, B. Now they're different, but there's 1, 2, 3 zeros between the two. So it doesn't tell me an exact amount of zeros, but it is awesome to tell me if I have a 0 in between them. It's super great if this is a radical or some kind of non-terminating decimal for that. So find the zeros. The first thing I want to do when I find zeros is you have to factor. So factoring is key. And we've actually done this stuff before. So I look for the greatest common factor, which is x. Okay, then I factor this in here. Factors of 2 that subtract 1. That's 2 and 1. Signs are different. The bigger one is positive. Oop, that's a minus. And then we're setting it equal to 0. We are finding when y is 0. So I have x equals 0, x minus 1 equals 0, x plus 2 equals 0. Okay, so x is 0. There's 1, 0. Add your 1, so x equals 1, and subtract your 2. Minus 2. Okay, so there's your other 0. So your zeros are 0, 1, and minus 2. Graphically, if we look at this, so we have x to the third plus x squared minus 2x. Get rid of that end one. So graphically, if we look at this here, okay, the parent function is a third, so it's got that s, and notice it crosses 1, 2, 3 times. Why? Because I have 1, 2, 3 zeros. Okay, if I go to my table, and if I plug in 1 here, I get a 0. If I plug in 0, I get a 0, and if I plug in minus 2, I get a 0. So I want to know when y is 0, and then I get those numbers right there. I mentioned multiplicity before. Okay, so multiplicity of a 0. If x minus the number to the n is a factor, then the number is a 0 with multiplicity of n. So that's when I wrote like x equals 5 m2. Okay. This would be the same as x minus 5 squared being a factor. And we've seen that before. Okay, so find zeros, multiplicities of that function. Okay, so these are my factors. So I'll set each factor equal to 0. So I can kind of ignore these powers here, because if I just take the square root, I get x minus 1 equals 0, x equals 1. But now I have to remember that power, because that tells me that it was a multiplicity of 2, meaning I had 2 factors of this 0. Okay, so I'll set this equal to 0, subtract 3/5. So 3/5 is 3/5 is a 0 with multiplicity of 7. Okay. So find a polynomial of degree 7 with zeros. -2 multiplicity 2, 0 multiplicity 4, 1 multiplicity 1. Huge problem right here. Okay, I really like these problems. They're all over the test, quiz, everywhere. Okay, so make sure we know how to do this one. So what this means is that x equals -2 twice. So x equals -2, x equals -2. This means that x equals 0 4 times. Okay, and this means that x equals 1 time. Now, from this, I can get an equation, or I can get a function. We'll say f of x. Okay, so for these factors, I would say x plus 2 squared. I just add 2 to the other side. I get x plus 2 equals 0. And I've got it twice, so I've got that squared. I've got x equals 0, 1, 2, 3, 4 times. So I have x to the 4th, okay, because this is my factor. And then I have x minus 1 equals 0. I have that once. So x minus 1. So now all I need to do is factor all, or multiply this all out. Okay, so we'll FOIL this part. So that's square the first, multiply them all together, square the last, x to the 5th, distribute this in here, minus x to the 4th. Okay, so now I need to multiply all these together. So I've got x5 minus x4. We'll stack them up. So minus 4x4 minus 4x5 minus x to the 6th, 0. That's 4x5. That's 4x6. That's x7. We'll add down. So those cancel. You get x7 plus 3x6 minus 4x4. Okay. So I've got a polynomial of degree 7, and if I were to graph it, it would cross at these spots right here. So let's look at that. So if I graph it, so I have x to the 7 plus 3x to the 6 minus 4x to the 4th. Graph. So -2, 0, and 1. Now, if we zoom in just a little bit here, you'll notice it kind of does some funny stuff around those 3 points. Okay. And we'll get to talking about that here in just a second. Okay. Sketch the graph of x plus 2 times the quantity x minus 1 squared. Okay, so let's kind of review some of the steps we did the other day. So we want to find the y-intercept. Okay, that is when x is 0. Okay, so I've got 0 comma what? Okay, so if that's 0, then I get 2. If that's 0, I get minus 1 squared. So minus 1 squared is 1 times 2 is 2. So if I kind of start my graph over here, I have a point at 0, 2. Okay, if we want to find the x-intercepts, I set this equal to 0. So I can set each factor equal to 0. So x plus 2 equals 0. So x is minus 2. Here's my minus 2. And I have x minus 1 equals 0. So x is 1. But that one has a multiplicity of 2, but I can't graph it twice. Okay? So now I have 3 intervals here. Okay, we're going to kind of ignore that y-intercept. Okay, I've got 3 intervals. I've got this one, and this one. And I want to know what's going on in this interval right here. So I might just plug in a number in this interval. So let's see, 1, 2, let's plug in -3. So if I plug in -3, I have -3 plus 2, -3 minus 1 squared. So minus 16. So I'm at -3 minus 16, way down here. Okay, so that tells me that this graph has to be coming this way. Okay. Now I know here that it's above, so that means I'm coming this way. Okay, I might plug in -1. So -1 plus 2 minus 1 squared. I get 4. So a -1, 1, 2, 3, 4. So that's way up there. Okay. And then it comes back down to there. And then over here I might pick 2. So I've got 2 plus 2, 2 minus 1 squared. So 4. So back up here. So then it turns around and goes the other way. Okay. Well, notice here, so there's my sketch graph, and we can put it on here so we can see what it looks like. Okay. We know that it's a third. It's x to the third. Why? Because I've got a 1, and this would be a 2. So I've got 1, 2, 3. So x to the third, which forms that s, okay, from the parent function. So there it is. We can zoom standard. See a little bit better. Okay. Now, notice the multiplicity of this was 2, and what happened at 1? Okay, it kind of bounced off. The multiplicity of this was a 1, and what happened to it? It passed through it. Okay, and that's what we're going to talk about here. Using multiplicity with graph, if it is even, it's going to bounce, or what I refer to as kiss. It's going to go right to that number and bounce right off. It's going to kind of come up and kiss that line and return. Okay. If it is an odd multiplicity, it is going to pass through it or cross it. Okay, just like this one had an odd multiplicity. It was x equals -2 multiplicity of 1. 1 is odd, and it passed right through that. Okay, so this is important to know about your functions. Okay, so end behavior. End behavior is what happens at these arrows. That's my end behavior. As it goes on, what's going on with my graph. So we've got our certain degrees. We can either have odd or even degree. We can have A, or A is my leading term. Okay, A can either be positive, negative, positive, negative. Okay, and for example, this is x squared, this is minus x squared, this is x to the third, and this is minus x to the third. Now, what does the negative out front do? Well, that's a negative A. Negative A flips it upside down. So if we look at a graph here, okay, so x squared, negative x squared, x to the third, negative x to the third. So flip it upside down. Okay, so if it is even and the A is positive, what is happening to my end behaviors? Well, as x goes to infinity, y goes to infinity. So as this number here is getting bigger, so is that value there. As x goes to minus infinity, y still goes to positive infinity. So as my x numbers get smaller here, this y value is still going positive. Okay, now what happens if I flip it upside down? As x goes to infinity, y goes to minus infinity, and as x goes to minus infinity, y goes to minus infinity also. Notice that they're doing the same thing. Your y's are doing the same thing. Now, what do we think is going to happen here with odd? Well, if I look at x to positive infinity, what does my y do? Well, if I go this way in this quadrant, it's going up. So y is going to infinity. If x goes to negative infinity, y goes to negative infinity. As x goes this direction, my y values go down. Notice they're doing the same thing in this direction now. Okay? So here as x goes to infinity, y goes to negative infinity. X goes to negative infinity, y goes to positive infinity. Okay, so they've kind of flip-flopped there. This is the end behavior. Okay, this is what I want to know. As x gets bigger, as x keeps getting bigger, what is happening to my y? Kind of similar to domain and range, but it's domain and range at the end values, the end points. Okay. All right, last example here. So we're going to graph this function here. So the first thing we want to find is our y-intercept. Okay. So that turns that to 0. So that's when x is 0. So that's 0, that's 0. So I simply get 0, 0. 0, 0. Okay, so we want an x-intercept. So in order to do that, we want to factor this out. So greatest common factor is 2x squared. So I'm left with x squared minus 4. I can factor that as a difference of squares and set each one equal to 0. And x minus 2 equals 0. So x is 0. X is 0 on that. X is negative 2, and x is positive 2. I got 1, 2, 1, 2. There. Okay, so this 0, okay, because I had an x squared right there, that was a multiplicity of 2. And what happens with multiplicity of 2 is it bounces. So we're either going to bounce here, or we're going to bounce this direction. These both had a 1, so we're passing through it. Okay, so we're going to pass through this one, pass through this. So this was x to the 4th was my parent function. So that tells me it could look like this, or it could look like this one. Okay. In order to do that, we want to look at a value. Okay, my leading term. So a is bigger than 0, which means it is opening up. So I should know that, okay, it is an even degree with a positive a, so my end behaviors are doing this. So we're opening up, basically, is what's happening. So we can know over here, my end behavior, as x goes to infinity, y goes to infinity. As x goes to minus infinity, y goes to positive infinity. Okay? Now, we could pick some points in here. I might want to know how far down does this go. Okay? So we might put in -1. Okay? So if I put in x to be -1, and I might put in 1. What is y? So that's -1 to the 4th, which is 1, times 2 is 2, minus -1 squared is 1, times 8 is 8. So that was -6. And plug in +1, I have, that's 2 again, 1 squared is 1, so that's -6 again. So I'm here, and I'm here. So it looks like we're going to have some symmetry here. So again, it passed through there because I had a multiplicity of 1. It's going to turn around there, go back up. It bounces there because I had a multiplicity of 2. It's going to bounce there because it's got to go back up to that point. Okay. And again, if I cross, or if I double check that on the calculator, and graph it out, we notice that it looks very similar to what I have on my graph. Okay. So I've got maximums, I've got minimums here, and all sorts of that. Okay. Here are your suggested problems. Again, here's a challenge problem. Try it out. Make sure you've worked on these. Again, show up to class with questions. Okay. As always, this is at THS Mr. Jones signing off. Thanks for watching.